I was trying to give a catchy title because this is what's supposed to attract people, but we also want to talk about some stuff which are maybe a bit boring and difficult to explain to general public, or maybe not difficult to explain, but difficult to make you interested. So I hope I'm going to combine these two and give you a nice overview of what we do. This is not the job, this is not the project which is just my project. It's a collaboration between a lot of people, both from CREAM and SMRU Consulting, and SMRU as well. So I want to first talk about the concept of population consequences of disturbance, which I will refer to as PCOT. So basically, what we are trying to understand is how potential stressors, disturbing factor, and I can go back to it afterwards, eventually affects population dynamics. So how stuff happening at one end affects stuff happening at the other end. And there's this concept built by my colleague Enrico Pirotta, or concept which he nicely described in his paper, which basically tried to understand how to link these two. So what we are trying to do is trying to understand how stressors which affect individuals at the end results in population dynamics. And as you can see, there's many arrows in this graph, and you don't have to pay attention too much to the stuff. But basically what happens is that animals which are exposed to stressors, if this stressor doesn't cause an immediate death of animal, like for example, ship strike, it can affect its physiological change. For example, they are injured, or it can affect their behavioral stage. They can stop foraging, they can move away, they can stop talking to each other, etc. Then it has the effect on their health, and then ultimately vital rates, so the probability of reproducing or dying. And again, I will talk about it a bit more into details. So energetic path is just one of the paths. And this is what I'm going to focus during this talk, which is basically this orange route, where we assume that a stressor affects animals through behavioral change. In this talk, I will talk about stopping foraging, which means that you don't get as much energy as you would normally get because you just eat less. And that affects your energetical status, ultimately vital rates, and then population dynamics. Again, details afterwards. Okay, so because the talk is about the bioenergetic models, I would like to give you a short introduction of what it is about. And I put the word the dynamic in the bracket, and you understand why in a second. So imagine this is a pulpus. And basically, most of the bioenergetic models are built on the idea that they eat something, this energy they consumed is somehow distributed among different processes in their body, and then the leftovers are excreted. So basically, if you eat more than what you need, you get fat. That's the same exactly for marine mammals. If it's opposite, if you eat less than what you need, you get smaller. For marine mammals, it's very important because they use their excess energy to produce a very thick layer of blubber. And it not only has a function as their energy store, but it's also very important as a thermoregulatory layer, because it's basically like wearing a coat all the time. And it matters because North Sea or seas, waters around the UK are not very warm. Reality is a little bit more complicated than just in and out. So most of the bioenergetic models, they assume that it's not like that you get 100% of energy from what you eat. You have some sorts of digestive capability, and the easiest example are all of the ruminants. Like you eat a lot of grass, but you actually don't get much out of it. And then there's this whole part, what happens inside the body of the animal, which is this allocation of energy into different processes. And orders of these processes do matter. So you first use most of your energy to cover your basic maintenance costs. So keeping your muscles running, keeping your vital organs, and then also being able to function with normal stuff like walking, eating, sleeping, etc. As I mentioned, for marine mammals, they actually spend some energy on thermoregulation. It's depending on the species and time of the year, etc. But it's quite important that these things are happening in order. So assuming that this is 100%, if you spend, let's say, I'm making it up, 60% on the first 3 processes, you're only left with X, or 40% for the other one. And these are the ones which are important for us to understand. So how much energy animals have or are left for them for reproduction, which is important for population growth, for their growth, especially if they are juveniles or pups or calves. And then again, what's the relationship between how much energy you spend on all of these processes and how much you are able to convert into this blubber layer. And again, why is it dynamic? It is dynamic because there's a huge variation in how much energy you get in. It's both natural variation and anthropogenic variation, and I'll go back into a second. But also there's a variation in out. So this varies in time and space. I'm not going to talk too much about space, but time in general. So for example, if you're a juvenile, you don't reproduce, you spend most of your energy on growth. But if you're a reproducing female, this is the part which takes up quite a lot of your energy. So what can vary with disturbance? And again, into details in a few slides. So disturbance can affect both so how much energy animals acquire, but they can also affect how much energy is allocated to these different processes. So what are the natural variation in? And I'm going to focus on 3 local species, just because the UK is a coastal, or it's actually a big island, so there's a lot of coastline, and these 3 species are the most common marine mammal species around here. Actually, harbor seals and grey seals you can see in Tensmere if you are lucky, especially grey seals. So 3 most common marine mammal species, which is harbor porpoise, harbor seal, and grey seal. And how this differs for these 3 species. So porpoise is a species which spends entire water on land. It's in water. It's born in water and breathes in water. It dies in water. So basically, and on top of that, it's an animal with extremely fast metabolic rate. So they eat constantly. When I mean constantly, some of the studies show that they can catch up to 1,000 little fish per day. And this is what they do. So they are extremely dependent on, or maybe let's put it this way, they're extremely vulnerable to this variation in. Seals, on the other hand, they rely a little bit more on their blubber. And then harbor seals, when they produce pups, they actually don't feed for the first few days when the pup is born. So the mom is giving milk to the pup, and it's on land all the time. Grey seals are even more extreme because they don't feed through the entire lactation, which is usually 3 weeks. And on top of that, seals are going on land sometimes. That's where we see them. So they don't eat when they're on land. And then once per every year, they change the entire fur. They molt, and during molting, they also don't eat. So there's this kind of temporal variation in. On top of that, there's of course variation in how much fish is at sea and how are these animals able to find food. There's also natural variation in out, so how much energy is allocated. And these are the graphs showing changes in body condition, which is basically proportion of fat in comparison to your total body weight for the 3 species. So we have grey seals, harbor seals, and harbor porpoise. And then the red ones show the offspring, so pups or calves, and the black ones show females. So for example, for grey seals, I told you that they don't eat when they lactate. So here the pup is born. You can see my mouse, yeah? Okay, good. The pup is born, which means that pup is gaining a lot of energy in a very short time. We are talking here about 2 weeks because the milk is very rich. But at the same time, mom is getting very skinny. Then the pup is weaned, and the mom goes back to sea and keeps foraging to gain the same energy level as before giving birth. For harbor seals, it's a little bit less extreme because I told you that the females, they go back to sea even if the pup is not weaned yet, but you can still see that they have this quite a big dip in energy. Porpoises, on the other hand, because the calf is with the mom all the time, because they are at sea, this variation is somehow not as extreme. So what does it help us to understand when we build these bioenergetic models? It helps us to understand that there are some periods in life for each of these individuals which are very critical for them. So if you disturb females at the time when their energy is lowest, that will have a very different effect than when you disturb females at the time when they are quite well. And that's the same for us, yeah? We can, if you are really tired, you can't eat or have a break for several hours. You want to go and eat, yeah? But if you just had a large meal and you are in good condition, you can probably keep going for a few hours, yeah? So it's the same for animals. If they are in a good energetic status, their reaction to disturbance will be different than when they are at their, let's say, most critical time. So again, this is important for this whole chain of processes, because it affects reproduction, and if it affects reproduction, it means maybe less offspring is born, and then it means the population is going down. Okay, but we are talking here about disturbance. So how anthropogenic influence can affect in. So it's not very surprising for you that sea is a very noisy environment, and there's plenty of anthropogenic sources of noise, because this is about energy. And also we at SMER Consulting and CREAM work a lot with offshore energy. This is one of the main focus of our work. So it's how noise from construction of wind farms may affect marine mammals. But there are plenty of other sources of noise, regular shipping, but also seismic survey or naval exercises. And it is important, especially for stations, because they use noise to communicate. Noise propagates very, very well at sea or in water in general. So animals can communicate on very large distances, but they also use sound sound to catch prey. So porpoises use echolocation to catch their fish. So if you make the environment very noisy, they may simply not be able to find food. So we are trying to understand what happens if animals are disturbed for X. And here X, it's time, and it could be anything from hours to days to months. So basically, using these bioenergetic models, we can understand if you deprive animal for X number of hours or days or months from getting any food, how does it affect all of these processes I showed in the previous slide? Okay, so we can understand this variation in and out, but how is it related to population dynamics? So then it comes to this purple square, where we are trying to understand how this variation in and out affects, as I said, these last parts. So probability of females to reproduce, and also probability of any individuals to die, because ultimately this is the main input for population dynamics. If you know how many individuals is born, how many individuals is likely to die, you can understand how total numbers of individuals in population may change if something happens. Okay, so far I've been talking about how we can understand what happens if. But the question is, how likely is that if this if is going to happen? So imagine two hypothetical scenarios. The big blue line shows a range of a population, and then you have some sort of disturbing event happening in this blue circle. So for example, there is a piling happening, which means that all of the individuals within the range where noise is affecting their behavior, they, for example, have to flee from the area, which means they lose time for foraging. Or they are just excluded from the habitat, which used to be their favorite foraging site. And if we're talking about a nomadic population, or population consisting of individuals which move at long distances, we have a case where at the disturbing area at any time, we may have a lot of different individuals, but the same individuals is not likely to be very often within that circle because it moves far. On the other hand, if we are talking about resident population, we have cases where there are some individuals which spend their entire time within the disturbing range, or most of the time, but then there's plenty of individuals which may never come to the disturbing area. For example, porpoises are a mix of these two approaches. So when they are young, they usually travel quite far, so they are more nomadic. But when they can get older, they are usually constrained to not very large area. Harbor seals, on the other hand, are very local species. They rarely travel very far, so they are very resident. And then gray seals are somehow in between. Again, depends on the life stage, but also where they are around the UK. And I show you some tracking data afterwards. So how it may affect population dynamics. So we can have a case here where very few individuals are affected, but very severely. Whereas in this case, we can have larger number of individuals being affected, but each of them not very severely. So we are trying to understand how these two contrasting approaches, or how these two contrasting situations may affect the population dynamics. So that's why it's important to understand the movement of animals. And here are the lower two panels show the tracking data for the two seal species around the UK. And here you can see that gray seals, they like moving quite far, whereas harbor seals are very, very local, and they stay most of their life within one area. So together with my colleagues, we built, or we used movement models which were built by other colleagues to understand where animals can be at the given time and space. So this is the model for harbor seals, and we are somewhere here. Yeah, and this is the inner Danish waters, which is an area of very high density of porpoises. So basically, coming back to these two hypothetical situations of nomadic and resident, if we go back to the inner Danish waters, where, as I said, there's a lot of porpoises are actually within this red area. So if you understand the movement of animals within that red area, you can understand this probability of the resident individuals to be within disturbance area. At the same time, a bit north from that area, it's an area of relatively low density of animals, which means that a lot of individuals just pass by, so they would resemble this nomadic. So we used the information from the tagging and the information from the two movement models to come out with what we call probability of exposure. So how likely it is that you as a seal or porpoise can be in the area of disturbance. And for example, if we look at the area from here, again, we are somewhere here. This is the area of very high density for gray seals, and this is the area of quite a high density of harbor seals, relatively, because harbor seals are slowly, the population around this particular area is decreasing, but still relatively this is an area of high density in comparison to this black, which I don't know if you can see, where there's not many seals observed. So we can use these two approaches, the tagging and the models, to understand these graphs on top, which are what I describe as probability of exposure. So how to interpret it? If your probability of exposure is 1, you mean that you as an individual are in the area all the time. If it's 0, you are not there. And then something in between, it's whatever it's in between. So we can see that if a disturbance was happening in this low density area, most of the animals for whatever species, so we have gray seals, harbor porpoise, and harbor seals, most of the animals are never there. Whereas if you have a disturbance or a wind farm being built in the high density area, you can see that there's still quite a lot of individuals which are never there. But then there's a group of individuals which are almost always there. And then porpoises are somehow in between, where you have almost no individuals which are never there, if it makes sense. So the red one, close to 0, or the x-axis 0, is also it's also 0 on the y-axis. Okay, so how are we trying to use it in management and in combination with bioenergetic models? So we are trying to understand. That's not me. I don't know why it's there. We are trying to use this bioenergetic model to understand how this two most important factors affecting population dynamics, which is the birth rate and then the mortality, which would be offspring mortality and adult mortality. Okay, now my mouse is gone. Anyway, yeah, how it affects ultimately population dynamics. So on the x-axis, you will have this probability of exposure. It could be anything between 0.05, which is 5%, to 1. But on the y-axis is this x. So for how long you are likely to disturb animals, or for how long they are likely to stop foraging when you disturb them. And we don't really know for any of these species because it's very difficult to establish. So we use these models to try come out with a range of values. So anything from 1 hour to 12 hours, which would be half a day of continuous non-eating. So we use this combination of probability of exposure and duration of no eating to understand how these free vital rates are affected. And this is a hypothetical output where you would expect that if your probability of exposure is 1, so 100% of the time you are exposed to disturbance, and every time you're exposed, you stop foraging for 12 hours, your vital rate or the population level vital rates would be affected strongest. So in this hypothetical situation, you would have 80% decrease in birth change. So this is one extreme end. The other extreme end is here, where you are never there and you are disturbed for a very short time. So we are trying to find out where we are in this kind of spectrum. And it is important for management because we are automatically drawn to this corner, looking at the worst case scenario. But the question is, how likely is this worst case scenario? So these are the results, and I don't want you to pay attention to numbers because that's not very important here. But basically, as we expected, it shows that the larger or the higher the probability of exposure coupled with higher duration of disturbance or disturbance effect, so how many hours you stop foraging, the larger the effect. So again, as shown in this hypothetical situation. But then we color-coded this graph with what we found out here. So how likely it is that any of this probability exposure applies to your population. And you can see the darker, the more. So for example, harbor seals and gray seals, it's more likely that individuals are not at the area of exposure. Yeah? So basically, that means that looking at the upper right corner for this particular 3 species is maybe not the most accurate one. So we can slowly move from this worst case scenario to something more realistic if we have information on movement and bioenergetic. But we can also use the bioenergetic to, for example, guide developers of wind farms when to concentrate the piling. And again, I showed you in this graph when we tracked the body condition of animals that if you disturb, for example, porpoises in August when they breed, so when females are the most vulnerable because they have the lowest energy level because they have to feed their young, that's the time when piling would be most, would have highest effect for these individuals. So this is another project that what I'm presenting now, but this is just to point out that we can use these bioenergetic models as well to guide piling schedule. But the most important thing is to move from this worst case scenario to something a bit more realistic. For this particular 3 species, something in that 3 black windows. Okay, so to summarize, the energetic models can help us to understand how variation in energy intake due to disturbance may affect how much energy is left for different body processes. Ultimately, that affects vital rates and at the end population dynamics. They can help us to identify these critical periods during the year which animals are most vulnerable and how these critical periods differ between different species. They can tell us what happens if animals are disturbed for X, and hopefully with more and more projects we can understand what is the range of plausible X's. So are we talking about disturbance for hours or days? And also if you couple the bioenergetic models with the information on the movement, you can get a better picture of the probability of animals being actually exposed. Thank you.